All right.
Good morning, ladies and gentlemen. I'm Andy. It's Brian, Caleb, and Thomas, as you all know. Today we're going to present to you the design, construction, and failure of our Balsa Bridge. For our bridge design, we chose a simple girder-style bridge because it's easy to construct, therefore reducing the possibility of construction errors and imperfections. When we design our bridge, we design our girder to have the outer edges span 4 inches, which is also the width of the loading plate applied to the bridge. And the reason for this is to ensure that all the load transfers to the girders, which support the entire bridge deck. Girder bridges can be found in many highway overpasses and many other places because they're an effective and efficient design, quick and easy to build, and they're effective for short spans.
Like Andy said, we just did a 2-girder bridge, and basically all we did was we had a slab that was made out of 2 layers of the 1/8 inch balsa wood, and the top 2 had a seam in the middle, and we decided to put the seam in the middle on top instead of on the bottom. That way, whenever it was in compression, it would be holding together. And we staggered the bottom so that there was no continuous seam through the bridge deck. And our girders were made out of a bunch of the pieces glued together, and there were 10 of them wide, so it made it 1 3/8 thick. And whenever we glued them to the bridge deck, we made the glue seam perpendicular with the bridge deck, which made the force come down where each of the slats would have its highest moment of inertia and hold the most weight. And that's about it.
For the force path, the plate that was used was 4 by 8 inches, so the force was transferred from the bridge deck to the 2 girders and then to the 4 roller supports. We treated it as a one-way slab, so half of the entire load went to each girder. Then from the girders to the supports, half of the girder load went to each support, so a quarter of the entire load went to each support. Here's the shear diagram for it, and as you can see, there's a distributed load of 27 acting in the middle third of the span. We got 27 from our total load, which was 437 pounds. Divide that by 2 for each girder, and then divide it by your 8 inches, gives you the 27. The maximum shear occurred at the other 2/3 of the span because the entire load was transferred to each support. And our girders were designed to carry a maximum amount of shear because of the uniform shape across the length, which means that the moment of inertia was the same across the length, which allowed us to carry a large load but didn't help resisting deflection.
All right, as Caleb just mentioned, we were unable to resist a large amount of deflection, and therefore we had what was called a serviceability failure. As you can see, we pretty much were going to eventually go past our 1/2 inch maximum deflection. We had no structural failure whatsoever. Actually, when we unloaded our bridge, it went back to its original shape, and we would have had it, but we unfortunately broke it yesterday. We were messing around with it. And but we also, as you can see, we were having, like the previous group, a ductile failure, where you could tell that the members were under stress, and in a real world application, you could have gone in and repaired and rehabilitated the bridge. We also like the serviceability failure over an actual structural member failure because when you would have gone to repair this bridge, you could have added additional girders or added additional support. But if one of our girders would have snapped, we would have had to come in, support the bridge, take out the girder, and place in another girder.
Well, in that case, you probably would collapse the bridge and then we wouldn't want it to be cheaper.
Yeah. So we were glad it was a serviceability failure and not a structural failure. When we took a step back and looked at how we can make our bridge better, we obviously started looking at ways to decrease our deflection because that's what our main problem was in. So as we learned from the virtual work method that we've learned in this class, we know that you take the moment equations over the modulus elasticity and moment of inertia. So we could have obviously made our moment of inertia high for the whole bridge and made the girders thicker, but that would have added unnecessary weight. So as the moment, as you can tell, it's the greatest in the center. So we would have liked, if we could have gone back and built it again, to make our girders in the same shape as our moment diagram, and that would make it the most efficient way to resist deflection without adding unnecessary weight. And we also, as in the equation for moment of inertia for a rectangular cross section is 1/12 base, 8 base times height cubed. When our height is taller, that makes much more effect than base. We also could have made our girders probably a little bit thinner, and that would have reduced weight also and cut down on our cost because a sheet of balsa wool is like $2. So, and we didn't have a structural failure, but we thought if we're going to apply this bridge to a railroad application, we could make some changes that would make the bridge safer. We eliminated redundancy in our bridge so that we could reduce weight for our testing. But in the real world, you would never design a bridge with just 2 girders because if one girder failed, the whole system would have failed. And those are actually known as fracture critical bridges, and they have to be inspected a lot more frequently than non-fracture critical bridges in the real world. So we would have probably added 2 or 3 girders, and that way we could have redundancy if, say, one girder had construction imperfection, or if one girder, the material wouldn't have been as well made, we could have, the whole system wouldn't have collapsed. And that's about all we thought that would be the best way to fix our bridge. And this is how much we trust our bridge. This was yesterday. And we actually didn't break it at this point, but I'm actually underneath the bridge, so
I saw that, I'm like...
so yeah, Andy actually broke it over his head. Anyway, but yeah, that's how much we trusted our bridge, and Andy does weigh a couple 100 pounds. So, and that's it. Do we have any questions, comments, discussion?
We have time for one question.
How'd you guys come up with that design? Just from driving on the bridges?
Yeah, it's simple.
Yeah.
Yeah, it was,
Caleb came up with it?
Actually, Brian did.
yeah. Well, I actually I worked with I co-op with a company, Infrastructure Engineers, when we do bridge inspection, and I just noticed that almost every highway bridge is built in girder style. You're not driving down the highway, you see those all the time. You don't see trusses everywhere.
Yeah.
And we just figured if we were going to have to build it, we obviously aren't master craftsmen, so building this is a lot. We reduce the risk for having any type of construction imperfection in building that design, rather than trying to have like a joint failure or something on a big truss.
Very good.
All right.
Let's